Hey guys, my name is Shayan. I'm a graduate student who has a certain interest in math, and so we're just going to talk about more math today. And today we're going to talk about two methods to evaluate Gaussian integrals. And so what's a Gaussian integral? It's a functional form that looks like this. And if you guys have taken like a stats class or probability theory, you notice this is a normal distribution. So if you're in like a college class and your professor curves, they usually curve to a normal distribution where some people here have like really high grades, most of the people lie in here, and then there's some people with really low grades, and these people like get A's, everyone else gets like B's or C's, and then like lower. So just some context, but a Gaussian is a functional form like this. So if this is f of x, then your function is e to the minus x squared. Okay, and so we just want to integrate this. And you notice that it's not really considered an elementary integral because you can't really integrate this by just looking at it. You can't integrate by parts. You can't use U substitution, trig substitution, stuff like that doesn't readily work because of this x squared here. So we're going to do it two ways. And we're going to start with this one first. Okay. Before we start, notice that this is an even function because of x squared. So we can always write this, instead of a symmetric interval like this, we can write it from 0 to infinity, e to the minus x squared dx. Okay, so the first method to solve this is the most common one, and it's using polar coordinates. Okay, and so what you do is you call this first integral I. And then you write I squared and put another integral that's exactly the same, but use a different dummy variable. And the variable you use does not matter, right? Because it's just integrated over. So these will give you the exact same values out. And so now we're thinking about polar coordinates here. So we want to think about r and theta. And we notice here we have x squared and y squared. So if we wanted to make something in terms of r, we know that r squared, which is the radius in polar coordinates, if we had a circle, would be just x squared plus y squared, right? It's just circle, here's r, here's x, here's y. So r equals the square root of x squared plus y squared by Pythagoras' theorem, and then this is that. So we're just going to combine these integrals. And so we're going to have a double integral. Okay, and so now it's going to be, and this is I squared, and we're just going to change it to polar coordinates using r squared. The only thing is when we change to polar coordinates, we have to change the differentials here, and you use something called the Jacobian. And so we're going to change from dx dy to dr d theta, but it's not a direct translation, right? There's some factor that we need in front of here, and that factor, I'm not going to derive it, but I'm going to write it. It's just the determinant, partial x, partial r, partial x, partial theta, partial y, partial r, partial y, partial theta, dr d theta. Okay. And so you know what x and y are, right, in terms of r and theta, because we're in polar coordinates. So x equals r cosine theta, and y equals r sine theta. So let's just calculate this. If you're interested in me deriving this, then please leave a comment, and I will show you the derivation for this, but we're going to just focus on the integral for this video. So dx dr is just take the derivative of this with respect to r. So we're just left with cosine theta. Dx d theta is minus r sine theta. Dy dr is sine theta. And dy d theta is r cosine theta. Okay, and so we have dx dy. And so this becomes an equals now. And then there would be a dr d theta, tacked on here. Just there's a dr d theta there, okay? No room. So then we do this determinant, And so we take the cross terms and multiply them. So we have r cosine squared minus a minus r sine squared. So this becomes, up here, just dx dy equals r cosine squared plus r sine squared dr d theta. And so we notice here, just factor out an r cosine squared plus sine squared is 1. So that's r dr d theta. Okay, so now back to our integral. This becomes an integral. Now our limits change also because we were going from x and y and we were going from minus infinity to infinity. So in that case, if we were in the xy plane, then we're talking about all of x and y. So we're going from minus infinity to infinity, minus infinity to infinity. So it's all of x and y. So in terms of r and theta, our r is our radius. So it starts at 0. And we want all of space, so we go to infinity. Our theta here, to get all of space, we're going to integrate over 2 pi, right? If we take r to infinity, theta to 2 pi, then we get all of space. All of r2, x and y. So now we have e to the minus r squared. Our Jacobian is r dr d theta, r dr d theta. Okay, so now we've taken an integral that we couldn't do, and we've taken it to an elementary integral where we can just do u substitution on. So now, I'm just going to erase this stuff. And so we don't have anything in terms of theta, so the integral over theta just becomes 2 pi. So we'll take this up here. Integral over theta is just 2 pi, and we just have this integral over r, which we can just do using a u sub. And so we let u equal r squared, and du equal 2r dr. And so we have 2 pi. And so we notice our limits of integration are still from 0 to infinity for u. They don't change. R is, well, r dr is du over 2. So over 2 du. And then e to the minus r squared is just now e to the minus u. Okay. And so 2's cancel. This integral itself, it's just 1. We can just really quickly show it. But then we do this, and this goes to infinity, so this goes to 0. Minus a e to 0 is negative 1, but then minus here. So you'll get 0 minus minus 1, so 1. Okay? So this integral is 1, 2's cancel, so this just becomes pi. And what we were doing here was I squared, so we have to be careful. Now I'm just going to write in here. So we say I squared is equal to pi. So our original integral here, I, that we cared about, was just this one. And so I is equal to the square root of pi. Okay, so that's this integral here. Again, like you could take plus or minus solution mathematically, but remember what our Gaussian was? It was this curve here. And if we think about the integral as an area under the curve, this is a positive integral. So taking the negative solution, we just throw it away. Okay? Okay. So this is a very common method. This is like, I think, the most intuitive way to do this. Not intuitive, this is pretty crazy. Like, it's a genius. Like, splitting it up like this and switching the polar coordinates is very creative, but this is the most common way. So we're going to do one more way, and this one's less common. But this one does not use polar coordinates. Okay, so our second method is called, well, we'll just define it. We'll just say it's a parametric method. Okay, so we're going to start with, this integral. We can interchange between these two integrals readily by just a factor of 2. So we're going to start by saying now our new s is equal to the integral from 0 to infinity, e to the minus x squared dx. Okay, and so we're going to start the same way and say s squared is equal to now the integral, the double integral from 0 to infinity, e to the minus x squared plus y squared dx dy. Okay, and so now the next thing to do is to make a substitution where, and this is why it's called parametric, because we're going to change from x and y to t and y. So the t comes from being parametric. So we're going to set x equal to ty, right? So then dx is equal to y dt. We're looking at this integral here now. So y is a constant, so when we just differentiate this, y stays constant. And so now we have integral 0 to infinity, and this one becomes an integral 0 to infinity. Still, x goes from 0 to infinity, t goes from 0 to infinity. E to the minus, okay, so now we're going to have ty squared. So we're going to take out a y squared and be left with t squared plus 1. All right, and then we have dt dy. And then a y that comes with the dt times y. Okay? All right. So now, because we're dealing with smooth continuous functions, we can switch the limits of integration. These are not dependent on t or y either. So we're just going to switch dt dy. And so this equals to integral 0 to infinity, integral 0 to infinity. And we're just going to switch these two. So e to the minus y squared, t squared plus 1, dy, y, dy dt. Okay, so now this is very similar to the Gaussian integral we just did with negative infinity to infinity, but now we're going from 0 to infinity. So we're just going to do a u substitution and find what that is. So again, u equals to y squared, t squared plus 1 this time. Du equals, so now we take the derivative of this with respect to y because we want to evaluate this integral here. So we get 2y t squared plus 1 dy. Okay, so now on the outside, we still have an integral from 0 to infinity dt. And now we have an integral e to the minus u, and we'll have du over 2 times t squared plus 1 in the denominator. Okay, and bounds now, y went from 0 to infinity, so u goes from 0 to infinity. Okay, almost done. So we have two integrals now, one in terms of u and one in terms of t. We can split it up again, smooth continuous functions. And again, t squared plus 1 is a smooth continuous function. If we look at the interval from 0 to infinity, right, it's just a 1 over t squared. It's just like this, right? But it's t squared plus 1, shifted up 1. So from 0 to infinity, it would just be smooth and continuous. Okay, but regardless, so if we pull the t squared out, we have two integrals, so 0 to infinity, 1/2, 1 over t squared plus 1, right? So pull this out, dt, and then integral from 0 to infinity, e to the minus u du. Okay, this one we've done, it's 1. This one, if you remember, is just 1/2 the arctan of t. And all we have to do now is evaluate it from 0 to infinity. So now we just kind of remember what the arctan looks like, or we remember its limits. So I'm just going to erase this here, and we need to keep that. So we'll just do it here. So arctan, it looks like this, where it asymptotes here at minus pi over 2 and pi over 2. So at infinity here, we see as t goes to infinity, this will asymptote to pi over 2, and at 0, it's 0. So here, we're just going to have pi over 2 times a 1/2. So we'll have pi over 4. Okay, and so our original integral is s. S squared we found was pi over 4. So that implies s is the square root of pi over 2. Okay, and so s we called this integral from 0 to infinity. Okay, and we got the square root of pi over 2. If we want to compare it to our original integral we did in the first example, then we just multiply it by 2, right? We just take the integral, multiply it by 2. It should give us the same value we got for here. So if we multiply this by 2, we get the square root of pi, and so we see it's consistent, just two different ways of going about it. I think this one's nicer because you don't have to deal in polar coordinates, and this is an elementary integral. You can just look up or whatever, arctan of t. Okay, that's it. Thanks for watching. Subscribe to my channel. Thanks to my cameraman and friend who were here for supporting. If you have any comments, questions, leave it in the description. Any problems with this, any more things you want to see, just shoot a comment. Don't forget to like, subscribe, and have a nice day.